the other comment we should make here is once I find zeta at T2, T3, T4, and T5, I also know that zeta of 0 equals 0. Suppose I should need to know zeta at some other date t. Well, then usually I use linear interpolation to get zeta in between the values of t. And usually in pricing you won't need to know it in between values, but if you do, just use linear interpolation. The question is, what does linear interpolation mean for the original problem? Well, remember that zeta of t is integral from 0 to t of the local volatility squared dt. Whoops. So all that means is that for my local volatility, when I use piecewise linear here, that just means I'm using piecewise constant here, right? So suppose I walk in some nice October morning and look, and this is my at-the-money swaption volatility matrix. Say fine. And suppose I choose kappa to be, say, 2%, right, which is sort of a standard value. I calibrate to the diagonal. It's not showing up here, but there is a bolder diagonal than others. It's a 10-year diagonal. The 1 into 9, the 2 into 8, et cetera, up to the 9 into 1. So I choose to calibrate on that diagonal, just as we said, to find zeta of 0, zeta of 1, zeta of 2, up to zeta of 9. Once I find the zetas, right, suppose I now use my closed form swaption formulas to find the dollar price for all the swaptions in the matrix, right? Not only the ones I've calibrated on, the bold ones, but all the other swaptions as well. Okay, this is the dollar price of swaptions. Now for each of these dollar prices, suppose I say, what's implied volatility do I need to put in a Black's formula to recover this dollar price? So this is where you gotta love Excel. If you do this, this is implied volatilities you've calculated from the dollar prices you got from the calibrated LGM model. So these are the theoretical implied volatilities for all the swaptions in the matrix. And now you know what comes next. We take, these are the theoretical prices, we subtract the prices we started with, and this is the error in the swaption prices for all the swaptions in the matrix. And look at this. If we look at this, we sort of have this warm and fuzzy feeling. Along the diagonal where I calibrated, of course, there is no error in the implied volatilities because I don't write that bad a code. Okay, I calibrated those things so the error is 0. But what's nice is look around it. All the swaptions that are anywhere close to the diagonal, the error is pretty close to 0, right? As a point of reference, the bid-ask spread for swaptions is usually known as 25 bips, which is 0.25%, and we'll want a bid-ask spread for anything near this diagonal. And that diagonal is really where this swaption is living. So you think, hey, maybe we got a chance at getting a decent price out of here. Okay. Well, that's fine. So, but that required us to put in this constant kappa, right? 2%, 3%, whatever we chose it to be. So let's set that aside a minute because we had this question mark over this constant kappa. And let's say, what's another method we can do? Well, this is a method that was invented at Salomon Brothers, supposedly. And in the old days, working for Salomon Brothers is sort of like being at Goldman Sachs now. You have to be a little bit smarter than everybody else in the world, right? Or at least that's the reputation. So the Salomon people, they said, well, okay. For hedging instruments, of course, we're going to calibrate on the diagonal swaptions at 2 into 4, 3 into 3, etc., 4 into 2, okay, etc., and at 8%. But then they say, all we want to assume now is we want to assume that the accumulated volatility is linear in time. And they phrase that something fancy like, we believe that uncertainty enters the marketplace at a constant rate, blah, 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 whatever. They mean zeta of t is linear in time. So it's alpha naught squared of t for some alpha naught. Or at this point, well, you can use your multiplicative invariance to choose what alpha naught should be. Make any choice you want. Here's my choice, 10 to the minus 2. You say, why is that? Well, basically, because the standard deviation is the standard deviation of interest rates, and basically rates go up by 1% or down by 1% a year, from 3% to 4% or 3% to 2%. And so if I let this be 10 to the minus 2, hopefully all the other numbers in the model work out to be sort of order 1-ish. Right? Okay, I use my additive invariance to set h of t6 to 0. And then when you calibrate the 5 to 1, you say, okay, we know zeta t5, we know of h of t6, there's only one unknown parameter, h of t5. Calibrate it, set the swaption to its market price, that determines h of t5. Then we roll back to the 4 into 2. Zeta t4, there's only one new unknown parameter, h of t4. Calibrate the 4 into 2 to its market price. Same thing for the 3 into 3 and the 2 into 4. And once you do that, you have h at t2, t3, t4, t5, and t6. Should you need to know h at any other values of t, use linear interpolation again. And what does that mean?